There is a point in the death of a massive star where the physics we learned in school simply stops working. A point where the ordinary rules governing matter, the ones that keep your desk solid, the ones that keep your bones from crumbling under their own weight, those rules get shredded, overruled, thrown out entirely, and in their place, something stranger and more fundamental takes over. Something rooted not in chemistry, not in molecular bonding, not in anything we can touch or see in the everyday world, but in the deepest, most counterintuitive principles of quantum mechanics. The object left behind after this catastrophe is roughly the size of a city. It has a diameter somewhere around 20 kilometers, give or take. You could drive across it on a highway in about 12 minutes, and yet this city-sized remnant contains more mass than our entire sun. It is so dense that a single teaspoon of its material would weigh around 1 billion tons on Earth. It spins, some of them, hundreds of times per second. It generates magnetic fields so powerful that they would distort the very atoms of your body long before you could get anywhere near the surface. It radiates energy in pulses so precise that the scientists who first detected those pulses genuinely considered, seriously considered, that they might have stumbled onto a signal from an alien intelligence. This object is a neutron star, and it sits, quietly, at one of the most extreme boundaries that matter can reach before ceasing to be matter in any form we would recognize. But here is the question that almost nobody stops to ask. Not the question of what a neutron star is, or how it forms. Those are remarkable stories in their own right, and we will get to them. The question almost nobody asks is the one that cuts to the very heart of what we understand about physics and gravity and the nature of the universe. Why doesn't it collapse? It has more than a solar mass of material compressed into a sphere 20 kilometers wide. Gravity is pulling every gram of that material inward with a force so stupendous it defies easy description. There is nothing holding it up in any conventional sense. No fire, no fusion, no heat engine running at its core. The nuclear furnace that kept the original star alive for millions of years burned out long ago. By every intuition we carry from ordinary experience, this thing should be falling inward. It should be collapsing. It should, in the span of a fraction of a second, crush itself down into a singularity, into a black hole. And yet, it doesn't. It sits there, stable, balanced, enduring for billions of years without collapsing. The answer to why involves a principle so strange that even physicists, when they first encountered it, struggled to accept what it was telling them. It involves a law of nature that says two identical particles of a certain class simply cannot occupy the same quantum state at the same time, not because they are bumping into each other, not because of any force between them in the conventional sense, but because the universe, at its most fundamental level, forbids it. The universe enforces a kind of cosmic exclusivity on certain types of particles that has no analogy in our everyday experience. Understanding how that principle holds up an object with more mass than the sun, and understanding exactly when and why it fails, plunging the remnant into a black hole, is one of the most profound journeys you can take through modern physics. If you enjoy deep space explorations like this, consider subscribing. Let us begin not with neutron stars themselves, but with the stars that create them. Because to understand the answer, you first have to understand the problem. You have to understand what gravity is actually trying to do to all stellar matter, all the time, throughout the entire life of a star, and why the final confrontation between gravity and quantum mechanics produces something as extraordinary as a neutron star rather than immediate collapse. A star is, at its core, a machine for resolving a tension. On one side of the tension is gravity, the inward pull of all that mass on itself. On the other side is the outward pressure generated by nuclear fusion happening in the star's core. For billions of years, these two forces negotiate. Gravity pulls inward, fusion pushes outward, and the star finds an equilibrium. This is called hydrostatic equilibrium, and it is the reason stars maintain their spherical shape and relatively stable size throughout their main sequence lives. But this equilibrium is always temporary. The fusion fuel, predominantly hydrogen in main sequence stars, is finite. The star is continuously converting mass into energy through fusion, radiating that energy as light and heat. Slowly, over geological timescales, the hydrogen in the core depletes. When it does, something significant happens. The core begins to contract because the outward pressure from fusion weakens, and as it contracts, the temperature rises. And when the temperature rises high enough, a new fusion reaction ignites. Helium, the ash product of hydrogen fusion, begins fusing into carbon and oxygen. This pattern, fuel depletion, contraction, heating, ignition of a new fuel, repeats several times in the life of a sufficiently massive star. The star moves through a succession of nuclear burning stages: hydrogen, then helium, then carbon, then neon, then oxygen, then silicon. Each stage produces heavier elements as ash. Each stage is shorter than the last because heavier nuclei release less energy per fusion reaction, and the star must burn fuel faster to maintain pressure against gravity. When a massive star reaches the silicon burning phase, the final stage, it is producing iron and nickel in its core, and iron is the end of the road for energy release through fusion. Iron sits at the bottom of the nuclear binding energy curve. Fusing iron requires an input of energy rather than releasing energy. There is no further nuclear reaction that can generate the outward pressure needed to fight gravity. The iron core grows. It grows until it reaches a critical mass, approximately 1.4 times the mass of the Sun. This is the Chandrasekhar limit, and its origins lie in quantum mechanics, which we will discuss in depth shortly. When the iron core hits this mass threshold, something catastrophic and almost instantaneous happens. In less than a quarter of a second, the core that took millions of years to build collapses inward at roughly 1/4 the speed of light. What happens in that fraction of a second is one of the most energetically violent events in the observable universe. The outer core falls inward so fast that the infalling material hits the incredibly dense inner core, now compressed to nuclear density, and bounces. This bounce generates a shock wave that propagates outward through the star with almost unimaginable energy. This shock wave is the supernova, but let us focus on what is left behind. After the explosion tears the outer layers of the star away, scattering them across light years of space as a glowing nebula that will eventually seed new solar systems with heavy elements. After all of that, the collapsed core remains. This is the proto-neutron star. It is hot, incomprehensibly hot, trillions of degrees in some models, and it is dense, and it is radiating neutrinos at a rate that carries away more energy in 10 seconds than our sun will emit as light across its entire 10 billion year lifespan. And then it cools over seconds and minutes and hours. The proto-neutron star settles. The neutrino flux diminishes. The surface temperature drops to something that is still millions of degrees, but comparatively settled. And what remains is this extraordinary, stable, city-sized object. But stability implies balance. Stability implies that some force or pressure is holding the neutron star up against gravity. What is it? To answer this, we need to take a careful journey into quantum mechanics. Not the popular science hand-waving version, but the actual physics laid out in a way that builds genuine intuition for what is happening inside a neutron star. The fundamental insight begins with a property of particles that has no classical analog. In quantum mechanics, every particle, every electron, every proton, every neutron, every quark has associated with it a set of quantum numbers. These quantum numbers describe the particle's state, its energy level, its momentum, its spin orientation, and other properties. Think of quantum numbers as a kind of address for a particle in the space of all possible states. Now, particles in the universe can be divided into two fundamental families. The first family is called bosons. Bosons have integer spin, 0, 1, 2, photons. Particles of light are bosons. The Higgs particle is a boson. Bosons are social particles. Multiple bosons can, and indeed prefer to, occupy the same quantum state. This is why lasers work. Vast numbers of photons can all be in the same quantum state, moving in the same direction, with the same frequency, coherently. The second family is called fermions. Fermions have half integer spin, 1/2, 3/2, and so on. Electrons are fermions. Protons are fermions. Neutrons are fermions. And fermions are antisocial in a very deep and specific way. No two identical fermions can ever occupy the same quantum state simultaneously. This is the Pauli Exclusion Principle, formulated by Wolfgang Pauli in 1925, and it is not a guideline or a tendency or a statistical preference. It is an absolute prohibition built into the fabric of quantum field theory. The mathematics of fermion states is anti-symmetric. If you try to write down a quantum state with two identical fermions in the same quantum state, the mathematics gives you zero. The state has zero probability of existing. It cannot occur. The reason for this connects to a deep theorem in quantum field theory called the spin statistics theorem. Without going into the full mathematical derivation, the essential point is this: the way fermionic quantum fields behave under certain mathematical transformations, specifically rotations and permutations of identical particles, forces the anti-symmetry that produces the exclusion principle. It is not an arbitrary rule. It emerges necessarily from the combination of special relativity and quantum mechanics, and the consequences are enormous. The Pauli Exclusion Principle is why atoms have the shell structure they do. It is why the periodic table has the pattern it has. It is why chemistry exists at all. If electrons could all collapse down into the lowest energy state, every atom would behave the same way. The variety of chemical elements would vanish, and the material universe as we know it would be impossible. But for our story about neutron stars, the critical consequence is this: when you compress fermions, when you force them into a smaller and smaller volume, they resist. Not because of any repulsive force between them in the classical sense, not because they are pushing each other away electromagnetically. They resist because compressing them forces them into the same region of space, which means they need to be in different quantum states. And since the available low energy states are limited, new fermions being pushed into the system must occupy higher and higher energy states. Higher energy state means higher momentum. Higher momentum means the particles are moving faster. Faster moving particles exert more pressure. This resistance to compression is called degeneracy pressure, and it is unlike anything in classical physics. Classical pressure, the pressure in a gas, say, depends on temperature. Heat a gas, it expands. Cool it, it contracts. The pressure in a normal gas is fundamentally tied to the thermal motion of its particles. Remove the heat, remove the pressure. Degeneracy pressure is different. It is quantum pressure. It exists even at absolute zero temperature. It does not depend on heat. You cannot cool it away. It arises purely from the Pauli Exclusion Principle and the requirement that fermions occupy distinct quantum states. It is, in the most literal sense, a pressure generated by the laws of quantum mechanics rather than by heat. This is what holds up a neutron star. But let us build our way to neutron stars carefully, because there is a step in between, one that both illuminates the physics and shows its limits. When a star with less mass than about 8 times the Sun exhausts its nuclear fuel, it does not undergo a core collapse supernova. Instead, it gently, on astronomical timescales, expels its outer layers as a planetary nebula, leaving behind a much smaller remnant called a white dwarf. A white dwarf is held up by electron degeneracy pressure. It is, essentially, an enormous quantum object, a body roughly the size of Earth, containing roughly the mass of the Sun, supported entirely by the refusal of its electrons to be compressed into the same quantum state. The electrons in a white dwarf are not fusing. They are not reacting in any nuclear sense. They are simply packed in, quantum states fully occupied up to what is called the Fermi energy, and they are exerting pressure by virtue of being fermions in a small space. A white dwarf can persist essentially forever. It slowly cools over billions and billions of years. Some white dwarfs in the universe are old enough that they have become quite cool, but their structure is unchanged. The electron degeneracy pressure does not depend on temperature, so cooling does not cause collapse. But there is a limit. In 1930, a young Indian physicist named Subramanian Chandrasekhar, 20 years old, on a steamship from India to England to begin his doctoral work, calculated something that would prove controversial, unsettling, and ultimately one of the most important results in astrophysics. He was working out the theory of white dwarfs, building on work by Ralph Fowler, and he recognized something that Fowler had not fully accounted for. When electrons are compressed tightly enough, their speeds approach the speed of light, and when you are dealing with particles moving at relativistic speeds, the relationship between momentum and energy changes. In classical mechanics, kinetic energy scales as the square of velocity, but in special relativity, at very high velocities, the energy scales differently. The pressure provided by relativistic electrons rises less steeply with compression than the pressure from non-relativistic electrons. What this means, Chandrasekhar worked out, is that there is a critical mass above which electron degeneracy pressure cannot prevent collapse even in principle. He calculated this mass to be roughly 1.4 times the mass of the Sun. Below this limit, electron degeneracy pressure holds up the white dwarf indefinitely. Above this limit, it cannot. This is the Chandrasekhar limit, and when a stellar remnant exceeds it, either through mass accretion from a companion star or because the original core was simply too massive, electron degeneracy pressure fails. The core collapses further. Now gravity has won the first round. Electrons are no longer sufficient to hold things up, but gravity has not won the fight entirely, because as the core collapses, something remarkable happens to the particles. The pressure and energy in the collapsing core becomes so extreme that a process called inverse beta decay begins to operate at enormous scale. Electrons are forced together with protons, a process that can be thought of as the reverse of normal radioactive beta decay, producing neutrons and neutrinos. The neutrinos, having extremely weak interactions with normal matter, stream out and away from the collapsing core, but the neutrons remain. In a matter of seconds, the collapsing core is converting its protons and electrons into neutrons at a catastrophic rate. The object that forms is not primarily a sea of electrons, it is a sea of neutrons, densely packed quantum mechanically degenerate neutrons. And now a new kind of degeneracy pressure takes over. Neutron degeneracy pressure. Neutrons are also fermions. They also obey the Pauli Exclusion Principle. They also resist compression because compressing them forces them into higher and higher energy states. And neutrons are about 1,836 times more massive than electrons. This matters significantly. When you confine a particle to a smaller space, quantum mechanics dictates that its momentum uncertainty increases. This is a consequence of the Heisenberg uncertainty principle, and therefore the particle must be treated as moving with higher momentum. But the pressure generated for a given momentum depends on the particle's mass. Heavier particles generate less speed for the same momentum, and less speed means less pressure. Wait, does that mean neutron degeneracy pressure is actually weaker than electron degeneracy pressure? In a sense, yes. For a given density, neutron degeneracy pressure is less than electron degeneracy pressure. But, and this is critical, neutron stars are far, far denser than white dwarfs. The neutron star packs its mass into a volume roughly 1,000,000 times smaller than a white dwarf. At those densities, the neutron degeneracy pressure is sufficient to halt collapse. The Chandrasekhar limit for neutron stars, by analogy, though the calculation is considerably more complex, is roughly 2 to 3 solar masses, depending on the equation of state of dense nuclear matter, a topic we will return to because it is genuinely one of the open frontiers of physics. Below this mass, neutron degeneracy pressure, E along with other nuclear forces, holds the star up. Above it, nothing can prevent collapse to a black hole. This is why neutron stars exist in the range they do, approximately 1.1 to 2.3 solar masses observed so far, with typical values around 1.4 solar masses. They are the survivors, the stellar remnants that were just massive enough to exceed the Chandrasekhar limit for white dwarfs, so electron pressure failed, but not so massive that they exceeded the TOV limit, which is what the equivalent limit for neutron stars is called, after the physicists Tolman, Oppenheimer, and Volkoff, who calculated it in 1939. Robert Oppenheimer, later famous for his role in the Manhattan Project, was, in the late 1930s, doing some of the foundational work in neutron star physics. He and his student George Volkoff calculated the structure of neutron stars using general relativity and, together with earlier work by Richard Tolman, established the maximum mass a neutron star can have. The result they got, roughly 0.7 solar masses, was actually too low because of simplifications in their calculation, but the approach was correct. Modern calculations, incorporating our much better understanding of nuclear physics, put the TOV limit somewhere between 2 and 3 solar masses. In 2010, astronomers measured the mass of a neutron star called PSRJ 1614-2230 using extremely precise timing measurements of its pulsar signal. They found it to be just under 2 solar masses. This observation immediately ruled out a number of theoretical models for the equation of state of dense nuclear matter. Those models predicted a lower maximum mass, and this observation showed they were wrong. In 2019, another neutron star, PSRJ 0952-0607, was measured at approximately 2.35 solar masses, the most massive neutron star currently known. It pushes the theoretical models further. Why do these mass measurements matter so much? Because the maximum mass of a neutron star tells us about the behavior of matter at densities we cannot reproduce in any laboratory on Earth. It is one of the few ways we have to probe the physics of nuclear matter beyond what particle accelerators can reach. Let us talk about what it actually means to be inside a neutron star, to stand, if such a thing were conceivable, at its surface, or to travel conceptually down through its layers. The surface of a neutron star, if you could somehow approach it, would be a remarkable environment. The gravitational field at the surface is roughly 200 billion times stronger than Earth's surface gravity. If you weighed 70 kilograms on Earth, you would weigh about 14 trillion kilograms on the surface of a neutron star. Every process happening near its surface is significantly affected by general relativistic effects. Light climbing out of the gravitational well is redshifted, clocks run slower, space itself is noticeably curved. The surface is solid, surprisingly, given what lies beneath. This outer crust is a lattice of atomic nuclei arranged in a crystalline structure, embedded in a sea of free electrons. At the very outermost layer, you have iron nuclei. Because iron is the most tightly bound nucleus, it tends to dominate the surface composition. As you go deeper, the density increases, and the nuclei become more neutron-rich because the high pressure forces electrons to combine with protons, converting them to neutrons via the inverse beta decay process we mentioned. Deeper still, at densities of around 4 times 10 to the 11th grams per cubic centimeter, you reach what is called the neutron drip point. At this density, the nuclei can no longer hold all their neutrons inside the nuclear potential. Neutrons begin to drip out of the nuclei and flow freely through the lattice. Below this point, you have a mixture of neutron-rich nuclei and free neutrons and free electrons. As you continue downward through the inner crust, the nuclei themselves begin to change shape. Instead of spherical clumps, they form cylindrical rods, then sheets, then the nuclear material may form a kind of sponge-like structure where the void spaces and the nuclear material swap their topology. Astrophysicists have given these exotic nuclear structures whimsical names: nuclear pasta. The cylindrical structures are called spaghetti. The sheets are lasagna. The sponge is the most complex and is sometimes called Swiss cheese, or, more technically, gyroid. Nuclear pasta is theorized to be the strongest material in the universe. Studies suggest its tensile strength exceeds that of steel by roughly 10 billion times, because it is essentially continuous nuclear matter rather than a bonded crystal of atoms. Deeper still, you enter the outer core, where the density exceeds nuclear saturation density, around 2.3 times 10 to the 14th grams per cubic centimeter, the density of an atomic nucleus itself. Here, discrete nuclei cease to exist. You now have a fluid of free neutrons with a small admixture of free protons, electrons, and muons. This is what most of a neutron star's interior is: a superfluid of neutrons threaded with a smaller current of protons that are themselves in a superconducting state. Neutron superfluidity is not a theoretical speculation. We have observational evidence for it. When a neutron star suddenly speeds up its rotation, an event called a pulsar glitch, the most compelling explanation involves a transfer of angular momentum from the superfluid neutron interior to the solid crust, superfluids have quantized vortices, and in the rotating neutron star, these vortices pin to the crystal lattice of the crust. Occasionally, large numbers of vortices unpin simultaneously and transfer their angular momentum to the crust, causing it to suddenly spin faster. The Vela pulsar, one of the most studied pulsars in the sky, glitches regularly in this way. It has glitched over 100 times since monitoring began, each time spinning up by a tiny but measurable amount. And then there is the inner core, the most mysterious region. At the center of a neutron star, densities may reach 5 to 10 times nuclear saturation density. At these densities, the individual identities of neutrons begin to break down. Remember that neutrons and protons are themselves composite particles. They are made of quarks. At extreme densities, the separation between individual nucleons becomes comparable to the size of the nucleons themselves. The quarks, which are normally confined inside hadrons, might begin to overlap, might begin to flow freely, rather than being locked inside neutron or proton structures. This is the regime of possible quark matter. If the core of a neutron star is dense enough, it may contain a fluid of deconfined quarks, a state of matter called a quark-gluon plasma. Though at the low temperatures of a neutron star interior, it would more properly be called color superconducting quark matter, a state where quarks pair up similarly to how electrons pair in a conventional superconductor. Whether neutron star cores actually contain quark matter is one of the great open questions in astrophysics and nuclear physics. We do not yet have observational data precise enough to definitively confirm or rule it out. The gravitational wave observations from neutron star mergers, particularly the landmark observation GW 170817 in 2017, have begun to constrain the possibilities, but the question remains open. There is also the exotic possibility of hyperon matter. Hyperons are particles related to protons and neutrons, but containing one or more strange quarks. In principle, the extreme pressure at the neutron star core could make it energetically favorable for some neutrons to convert into hyperons. This creates what physicists call the hyperon puzzle. If hyperons appear at high densities, they generally soften the equation of state, meaning the pressure increases less steeply with density, and this tends to reduce the maximum mass a neutron star can have. But we have observed neutron stars with masses close to or above 2 solar masses, which seems to leave little room for the softening that hyperons would cause. Either hyperons do not appear in neutron star cores after all, or there is some additional repulsive interaction between hyperons that stiffens the equation of state enough to reconcile theory with observation. This puzzle has not been solved. Let us take a step back from the interior physics and look at neutron stars from the outside for a while, because the observational phenomena they produce are extraordinary. The most famous manifestation of neutron stars is the pulsar. A pulsar is a neutron star that emits beams of electromagnetic radiation from its magnetic poles, and that happens to be oriented so that these beams sweep across Earth as the star rotates, like a cosmic lighthouse. Pulsars were discovered in 1967 by Jocelyn Bell Burnell, a doctoral student working with Anthony Hewish at Cambridge. Bell noticed an unusual regular signal in her radio telescope data, a pulse repeating every 1.337 seconds with extraordinary precision. The signal was so regular, in fact, that there was genuine discussion about whether it might be artificial. The research team initially, half-jokingly, called the source LGM1 for Little Green Men. It was quickly understood to be natural. Another pulsating source was found in a different part of the sky, and an artificial signal would not likely have 2 independent sources behaving similarly. But the brief consideration of an artificial origin tells you something about how precisely regular the signal was. The explanation came together over the following year. The source was a rotating neutron star. The regularity of the pulse, rivaling atomic clocks in its precision, comes from the extraordinary rotational stability of an object with so much angular momentum and so little moment of inertia. A neutron star is incredibly compact, so it has a very small moment of inertia. External torques that might slow it down or change its rotation rate have very little effect. The result is a rotating object of extraordinary stability. The fastest pulsars known are called millisecond pulsars. They rotate hundreds of times per second. The record holder, PSRJ 1748-2446 AD, rotates 716 times per second. Think about what that means physically. A sphere 20 kilometers across, containing more than a solar mass of material, completing more than 700 full rotations every second. At its equator, the surface is moving at approximately 24% the speed of light. How do pulsars spin so fast? For the fastest ones, the standard story is recycling. An older pulsar that has slowed down over millions of years accretes material from a binary companion star. That infalling material carries angular momentum, and as it falls onto the pulsar, it spins it up like blowing on a pinwheel. Over millions of years of accretion, the neutron star can be spun up to millisecond rotation periods. Recycled pulsars tend to be very stable rotators, and several of them are so precise that they are used as an astronomical tool. An array of millisecond pulsars distributed across the galaxy can function as a gravitational wave detector sensitive to very low frequency waves, complementing detectors like LIGO that are sensitive to much higher frequencies. The magnetic fields of neutron stars are another extraordinary feature. A typical pulsar has a magnetic field of roughly 10 to the 12 Tesla, roughly 1 trillion times stronger than Earth's magnetic field. Some neutron stars, called magnetars, have fields reaching 10 to the 15 Tesla. These are, to the best of our knowledge, the strongest magnetic fields existing anywhere in the universe. Magnetars were hypothesized in the 1990s and confirmed observationally through the study of anomalous X-ray pulsars and soft gamma-ray repeaters. These are neutron stars that do not derive their energy from rotation, as ordinary pulsars do, but from the decay of their immense magnetic fields. The energy stored in a magnetar's field is staggering, more than the sun will radiate over its entire lifetime. As the magnetic field slowly decays, it heats the star and powers sporadic, violent bursts of X-rays and gamma rays. In 2004, a magnetar called SGR 1806-20, located about 50,000 light-years from Earth, underwent what is called a giant flare. In 0.2 seconds, it released more energy than our sun emits in 250,000 years. Even at 50,000 light-years distance, this event was detectable from Earth and temporarily ionized the upper atmosphere. Had this magnetar been 10 light-years away, closer than the nearest stellar systems to Earth, the flare could have caused significant damage to life on Earth. It is fortunate that magnetars do not tend to form in our solar neighborhood. The magnetic fields of neutron stars are thought to originate from the amplification of the magnetic field present in the progenitor star during the collapse event. When the core collapses from a star perhaps 10 to 15 times the sun's diameter down to a 20-kilometer sphere, magnetic flux is conserved, and conservation of magnetic flux in a dramatically shrinking area means the field strength increases by roughly the square of the compression ratio. A modest stellar magnetic field of a few thousand Tesla becomes, after compression, by a factor of 10,000 in radius, a field of something like 10 to the 12 Tesla. The most extreme magnetar fields may additionally be amplified by dynamo processes operating in the convective, rapidly rotating proto-neutron star in the seconds after its formation. The surface temperature of a young neutron star is typically in the range of 1,000,000 degrees Kelvin, and it radiates primarily in X-rays. Over millions of years, it cools, but the cooling timescale is long, because the interior is in a state where heat transport is governed by highly exotic physics, including quantum effects in the neutron superfluid and the possibility of exotic cooling channels involving neutrino emission processes with names like the Urca process and modified Urca process. The Urca process, named, delightfully, after a casino in Rio de Janeiro by its discoverers George Gamow and Mario Schenberg, who felt that their neutrons were disappearing as fast as money at the casino, involves a cycle of beta decay and inverse beta decay that produces a stream of neutrinos carrying energy out of the neutron star. In the direct Urca process, a neutron decays to a proton, electron, and antineutrino. Then, the proton captures the electron to produce a neutron and neutrino. The neutrinos escape, carrying energy with them. This process can operate very efficiently in neutron stars with a sufficient fraction of protons in the core, perhaps above a threshold of around 11 to 15% of the particles being protons. If the direct Urca process operates, it cools neutron stars rapidly, perhaps too rapidly, judging by the temperatures of some observed neutron stars, which suggests the process is suppressed in those cases by superfluid pairing. Neutron star cooling is actually an observational window into the physics of the deep interior by measuring the X-ray luminosity of neutron stars of known age, particularly those in supernova remnants where the age of the remnant can be independently estimated. We can compare observed cooling curves to theoretical predictions. Some neutron stars are cooling faster than standard models predict, suggesting rapid cooling channels are operating. Others are cooling more slowly, suggesting superfluidity is suppressing the Urca process. The interplay between these observations and theoretical models is an active research frontier. There is also a beautiful connection between neutron stars and gravitational waves that deserves extended treatment because it opens up an entirely new way of observing these objects and illuminates the physics of their interiors. On August 17, 2017, the LIGO and Virgo gravitational wave detectors recorded a signal unlike anything they had seen before. Previous detections had all been from merging black holes, events where two massive, compact objects spiraled together and merged, releasing gravitational wave energy in a fraction of a second. The August 17th event lasted much longer. The inspiral phase was detectable for nearly 100 seconds before the final merger, and most remarkably, roughly 1.7 seconds after the gravitational wave signal ended, gamma-ray telescopes detected a burst of gamma rays from the same direction. This was GW170817, the first gravitational wave detection from a binary neutron star merger, and the coincident electromagnetic signal, gamma rays, then X-rays, then optical light, then radio emission, opened an era of what astronomers call multi-messenger astronomy. For the first time, an event was observed simultaneously in gravitational waves and in light across multiple wavelengths. The gamma-ray burst confirmed a theory that had been proposed since the 1980s. Short gamma-ray bursts are powered by neutron star mergers, but the optical transient that followed, called a kilonova, confirmed another long-standing prediction that neutron star mergers are a major production site for heavy elements in the universe through a process called the R process. The RR process, rapid neutron capture, is the mechanism by which the heaviest elements in the periodic table are created. When the neutron density is high enough, atomic nuclei can capture neutrons faster than they decay, building up very neutron-rich nuclei that then decay radioactively into stable heavy elements. Gold, platinum, iridium, uranium, the lanthanide rare earth elements, many of the heaviest atoms in the universe, are thought to be primarily produced in neutron star mergers. The kilonova following GW170817 was spectroscopically analyzed, and the results confirmed the presence of heavy R process elements. Strontium was definitively identified, and the overall light curve was consistent with the production of a significant mass of lanthanides and other heavy elements. Estimates suggest that this single merger may have produced something like 50 times the mass of the Earth in gold and similar quantities of platinum and other heavy R process elements. The gold in your wedding ring, the platinum in your catalytic converter, may well have been forged in a neutron star merger billions of years ago and scattered through interstellar space to eventually be incorporated into the cloud that became our solar system. GW170817 also provided crucial constraints on the neutron star equation of state. The gravitational wave signal from the inspiral phase carries information about the tidal deformability of the neutron stars, a measure of how easily the gravitational field of one star distorts the shape of the other. Compact hard objects are less tidally deformable. Larger, fluffier objects are more deformable. By analyzing the precise shape of the gravitational wave signal, physicists extracted a constraint on the tidal deformability parameter, which in turn constrains the radius of neutron stars. The result was broadly consistent with a neutron star radius of roughly 11 to 13 kilometers, tighter than most previous estimates, and ruling out some extreme equation of state models. The post-merger fate of GW 170817's remnant is also scientifically interesting and not fully resolved. The gamma-ray burst, detected 1.7 seconds after merger, suggests that the merger product collapsed to a black hole fairly quickly, maybe within a second. But there is some debate about whether it formed immediately or whether a supermassive neutron star supported by rapid rotation survived briefly before collapsing. The 1.7-second delay between the gravitational wave signal and the gamma-ray burst could be explained by a brief period of hypermassive neutron star existence, but the evidence is not conclusive. Future gravitational wave detectors, Einstein Telescope in Europe and Cosmic Explorer in the United States, both in planning or early development stages, will be sensitive enough to detect many more binary neutron star mergers. And crucially, if the remnant is a supermassive neutron star that survives for at least tens of milliseconds before collapsing, its rapid rotation will generate a gravitational wave signal at kilohertz frequencies that could in principle be detected by next-generation instruments. Such a detection would provide an extraordinary window into the most extreme phases of neutron star physics. Now, let us return to the original question with fuller context. We have established what holds the neutron star up, primarily neutron degeneracy pressure, supplemented by nuclear repulsion forces that become important at and above nuclear saturation density. We have established the rough boundaries within which this support is effective, but I want to deepen the understanding of exactly why this pressure is quantum mechanical in nature and why it cannot be cooled away, because this point is more profound than it might initially seem. When physicists talk about the equation of state of a material, they mean the relationship between pressure, density, and temperature, the relationship that describes how the material responds to compression and heating. For an ordinary gas, this is the ideal gas law. Pressure is proportional to density and temperature. For a more realistic gas, there are corrections. For a solid, the equation of state is determined by the bonding between atoms. For a degenerate Fermion gas, whether electrons in a white dwarf or neutrons in a neutron star, the equation of state is fundamentally different in character. In the limit of complete degeneracy, the equation of state depends only on density, not on temperature. The pressure is entirely determined by the density. This means that you cannot reduce the pressure by cooling the neutron star. This is profoundly different from every kind of support we encounter in ordinary experience. A hot air balloon stays up because the air inside is hot. Cool it, and it descends. A conventional gas-supported object loses its pressure support as it cools, but a neutron star, supported by quantum degeneracy pressure, can cool from trillions of degrees down to thousands of degrees over millions of years, and its pressure support does not diminish at all. The neutron star is held up not by thermal energy, but by quantum energy, the zero-point kinetic energy that fermions are forced to have by the Pauli Exclusion Principle. You cannot extract this energy by cooling because it is not thermal. It is the irreducible kinetic energy demanded by quantum mechanics of fermions that must occupy distinct states. This is why neutron stars are stable over cosmological timescales. They will not cool and collapse. They will not burn out and collapse. The only way to collapse a neutron star into a black hole is to add mass to it, either through accretion from a companion star or through merger with another compact object until its total mass exceeds the TOV limit. There is actually a fascinating class of objects, or hypothetical objects, that might exist between neutron stars and black holes in the mass radius diagram. These are sometimes called quark stars or strange stars, and they would be composed not of neutrons, but of quark matter, specifically a roughly equal mixture of up, down, and strange quarks. This is called strange quark matter, and there is a remarkable hypothesis, the Bodmer-Witten hypothesis, that strange quark matter might actually be the true ground state of matter at zero pressure. If this is correct, is ordinary nuclear matter, like the atoms of which you and I are made, is metastable. It is not in its lowest possible energy state. The lowest energy state of nuclear matter is strange quark matter. If this hypothesis is correct, then it is possible to have compact stars composed entirely of strange quark matter, strange stars. These would be self-bound objects rather than gravity-bound objects. Rather than being held together by gravity against internal pressure, they would be held together by the strong nuclear force itself, the same force that binds quarks inside hadrons. A strange star could, in principle, be much more compact than a neutron star of the same mass, because the binding energy per baryon is higher. Strange stars would be distinguished from neutron stars by their equation of state. They would be less tidally deformable for a given mass. Some observational hints have been interpreted as suggestive of strange star candidates, but nothing is confirmed. Beyond strange stars, there are even more exotic hypothetical objects: boson stars, composed of hypothetical scalar particles; preon stars, if quarks themselves are composite; gravastars, an alternative to black holes proposed by Mazur and Mottola. Most of these are highly speculative, and none have observational support, but they illustrate that the space between ordinary neutron stars and black holes may be richer than a simple one-step transition. Let us now also think about the endpoint of a neutron star's life in a different scenario. Not gradual accretion, but catastrophic merger. When two neutron stars in a binary system spiral together due to gravitational wave emission, shedding energy, and angular momentum as gravitational radiation, they eventually collide. What happens in that collision depends critically on their combined mass and on the equation of state. If the combined mass is below the TOV limit, which is possible for lower mass neutron stars, the merger might produce a rapidly rotating neutron star that is initially supramassive, supported against gravity, partly by centrifugal force as well as degeneracy pressure, but then collapses to a black hole as it loses angular momentum, or, with sufficient mass loss, through winds and tidal ejecta, it might settle into a stable, if rapidly rotating neutron star. If the combined mass significantly exceeds the TOV limit, the collapse to a black hole is rapid and perhaps nearly immediate. The dense nuclear matter that has been compressed far beyond any neutron star core density, deprived of any support, collapses in microseconds. G at W170817 seems to have been a case of relatively rapid collapse to black hole. The mass of the two neutron stars combined was about 2.73 solar masses, which likely exceeded the TOV limit, even accounting for the boost from rapid rotation. The transient signal expected from a supramassive neutron star, a bright X-ray and radio afterglow, powered by magnetar-like spin-down, was not strongly detected, consistent with relatively quick collapse. But the merger event does not just produce a compact object, it also ejects material. Some material is thrown off during the tidal disruption of the neutron stars as they spiral together. Tidal tails of neutron-rich matter flung into space. Some material is blown off in a wind driven by neutrino heating and magnetic fields from the remnant. Some material is launched in a relativistic jet. The total amount of ejected mass in GW 170817 was estimated at somewhere between 0.04 and 0.05 solar masses, a small fraction of the total mass, but representing a significant production of heavy elements when spread through the interstellar medium. There is a long-standing debate about the relative contributions of core collapse supernovae versus neutron star mergers to the R process enrichment of the galaxy. Both processes can, in principle, produce R process elements. But core collapse supernovae are far more frequent. They occur roughly 10 times per century in a galaxy like ours, while neutron star mergers occur perhaps once per 100,000 years. But each neutron star merger may produce far more R process material per event. The timing of heavy element enrichment in the early universe, gleaned from the chemical compositions of ancient stars in the galactic halo, seems to favor neutron star mergers as the dominant source, though the debate continues. The extraordinary interconnection between neutron stars and the chemical evolution of the galaxy is one of the reasons neutron star physics occupies such a central place in modern astrophysics. These objects are not just extreme laboratories for fundamental physics. They are key players in the chemical history of the universe. The matter of which we are made, including the iron in our blood, the calcium in our bones, and the gold in any jewelry we might wear, has a history that passes through the extreme physics of compact objects. Let us think now about what constrains the physics even further. What limits our knowledge of neutron star interiors, and what new observations might resolve those limits? The central uncertainty is the equation of state of dense nuclear matter. We know the equation of state reasonably well up to about nuclear saturation density. We can test it in terrestrial nuclear physics experiments and in relativistic heavy ion collisions. But above nuclear saturation density, and neutron star cores reach 5 to 10 times this density, our theoretical tools become less reliable. The perturbative methods that work at extremely high density, where QCD becomes asymptotically free, cannot be applied at intermediate densities, and nuclear many-body theory, while powerful, struggles at the highest densities. We are in a regime where we genuinely do not know what the correct description of matter is. The equation of state matters enormously for the macroscopic properties of neutron stars. A stiff equation of state, one where pressure increases rapidly with density, gives larger, more massive maximum neutron stars with larger radii. A soft equation of state, where pressure increases less steeply, gives smaller, less massive maximum neutron stars with smaller radii. Observations of neutron star radii and maximum masses therefore directly constrain the equation of state. The mass measurements we discussed, P SRJ 0952-0607 at 2.35 solar masses, are among the strongest constraints we have. They rule out soft equations of state. The tidal deformability measurement from GW 1708-17 constrains the radius, ruling out very stiff equations of state. Together, these observations are squeezing the allowed parameter space for the equation of state. The NICER telescope, Neutron Star Interior Composition Explorer, launched to the International Space Station in 2017, has added to these constraints by measuring neutron star radii directly through X-ray pulse profile modeling. NICER measures the X-ray emission from the hot polar caps of pulsars as they rotate, and the precise shape of the pulse profile carries information about the neutron star's compactness, the ratio of its mass to its radius. Early NICER results for the pulsar PSRJ 0030 plus 0451 found a radius of approximately 13 kilometers and a mass of about 1.34 solar masses. Results for PSRJ 0740 plus 6620, the previously most massive known neutron star at about 2.08 solar masses, found a radius of roughly 12 to 13 kilometers, consistent with a moderately stiff equation of state. What is remarkable about these observations is that they are beginning to paint a consistent picture. A neutron star of about 1.4 solar masses has a radius of roughly 12 to 13 kilometers. The equation of state is neither extremely soft nor extremely stiff. Quark matter in the core is possible, but not required. Hyperons might or might not be present. The data are not yet precise enough to definitively resolve these questions, but each new measurement helps. There is a deeper philosophical point worth dwelling on here. The physics inside a neutron star is fundamentally the same physics that governs the quarks and gluons in the experiments at particle accelerators, like CERN. The same physics that governs nuclear reactions in laboratory experiments on Earth. The same physics, quantum chromodynamics, nuclear many-body theory, general relativity, that we study in every other context. What is different is only the regime. The density and temperature inside a neutron star are beyond anything we can reproduce artificially. In a sense, neutron stars are experiments that the universe runs for us. They are nature's particle physics experiments, operating at energies and densities we will never achieve in a laboratory. Every neutron star is a probe of physics beyond what our accelerators can reach, and our ability to read the results of these experiments through pulse timing, X-ray spectroscopy, gravitational wave analysis, and other techniques is steadily improving. This is one of the reasons the era of multi-messenger astronomy is so significant. Gravitational wave detectors, X-ray telescopes, radio arrays, optical telescopes, each provides a different kind of information about neutron stars. Together, they triangulate the physics in ways that no single instrument can. The next generation of gravitational wave detectors, with sensitivities perhaps 10 times greater than current LIGO, will detect neutron star mergers at vastly larger distances, providing a statistical sample of events large enough to map the equation of state with high precision. Advanced X-ray telescopes will measure pulse profiles of many more pulsars, adding to the mass radius database. Next-generation radio telescopes will discover thousands of new pulsars in our galaxy, some of which will be in interesting binaries amenable to precise mass measurements. And perhaps most excitingly, the detection of gravitational waves from a post-merger remnant, the oscillating supermassive neutron star signal that has not yet been seen, would provide almost direct spectroscopy of the equation of state at the highest densities. There is something almost poetic about the situation. Here we have these city-sized objects floating in space at distances of hundreds or thousands of light years, and we are learning to read them. We are developing, painstakingly, and through the ingenuity of thousands of scientists and engineers, the means to extract from their pulsars and their gravitational waves and their X-ray spectra the deepest secrets of nuclear and quark matter. And at the center of it all is this remarkable answer to the question we started with. The neutron star does not collapse because the universe has a rule written into the mathematics of quantum field theory, arising from the geometry of Fermion statistics, that forbids two identical fermions from occupying the same quantum state. This rule, the Pauli Exclusion Principle, manifests at the scale of atoms as the structure of the periodic table and the existence of chemistry. It manifests at the scale of stellar remnants as the stability of white dwarfs and neutron stars. It is one rule, expressed at very different scales, and it is part of why the universe contains the variety and structure it does. Without the Pauli Exclusion Principle, white dwarfs would collapse to black holes. Without it, neutron stars could not exist. Without it, atoms could not have the shell structures they do, and chemistry would not work, and life would not be possible. The principle that holds up a neutron star is the same principle that makes your body solid. It would be wrong, though, to end the discussion of why neutron stars don't collapse without acknowledging the role of nuclear forces beyond degeneracy pressure. At the densities present in neutron star cores, at and above nuclear saturation density, the strong nuclear force becomes directly relevant in a way that goes beyond just binding quarks into neutrons. That between nucleons, neutrons, and protons, there are residual strong force interactions, sometimes modeled using exchange of virtual pions and other mesons. At short ranges, these interactions become strongly repulsive. This is what gives atomic nuclei their roughly constant density. You cannot compress nuclear matter much beyond its natural saturation density because of the short-range nuclear repulsion. In neutron stars, this nuclear repulsion provides an additional stiffening of the equation of state above nuclear saturation density, supplementing the neutron degeneracy pressure. The interplay between degeneracy pressure and nuclear forces is what theoretical nuclear physicists are working to model more accurately. The most sophisticated approaches use chiral effective field theory, a systematic expansion of nuclear forces derived from QCD, to compute neutron matter properties at moderate densities, then matched to perturbative QCD calculations at very high densities, with an uncertain intermediate regime in between. The goal is a complete theoretically consistent equation of state across the full density range of neutron stars. There is also the question of three-body forces. When three nucleons are close together, there is an interaction between all three that is not simply the sum of three pairwise interactions. These three-body forces are believed to be repulsive at high density, and they may be crucial for explaining why neutron stars can reach 2 solar masses. Some calculations suggest that without three-body forces, the maximum neutron star mass would be lower than observed. The same three-body forces have been measured in terrestrial laboratory experiments, in neutron-rich nuclei, and in nuclear reactions, providing a direct connection between laboratory nuclear physics and neutron star physics. The science is genuinely interconnected in this way. Let us also briefly touch on what happens to neutron stars over extremely long timescales, beyond what we have observed in the relatively short history of astrophysics. A neutron star in isolation, not accreting, not in a binary, will slowly cool. Its temperature will drop over billions and then trillions of years, eventually, as it will become what we might call a black dwarf of nuclear matter. Though since the universe at 13 billion years old is nowhere near the timescale where this has happened, it is entirely theoretical. On timescales of 10 to the 19 years or so, vastly longer than the current age of the universe, proton decay, if it occurs, which is predicted by some grand unified theories, but has not yet been observed, might destabilize the neutron star matter, turning it into something completely different. On even longer timescales, 10 to the 37 years or so, under some optimistic estimates, quantum tunneling might slowly convert the neutron star into a more thermodynamically favorable state. But these are not timescales that are physically meaningful in any practical sense. The universe as we know it will be vastly different, billions of times over, before such events could occur. For all practical purposes, a neutron star formed today will be stable for the age of the universe. It is one of the most enduring objects that can exist, more enduring than any ordinary star, more enduring than any planet. The same quantum mechanical principle that holds it up does not weaken with time. Now, let us widen our perspective once more and think about what neutron stars mean for our understanding of the universe as a whole. We live in a universe that has spent 13.5 billion years processing matter through stars. Every generation of stars fuses lighter elements into heavier ones, then disperses those heavy elements through supernova and other mass loss processes. Neutron stars are a kind of end-of-the-line product in this processing chain, compact repositories of nuclear matter that will persist essentially indefinitely. The Milky Way is estimated to contain roughly 1 billion neutron stars. Most of them are old, cold, and essentially invisible, no longer pulsing, no longer generating significant electromagnetic emission, simply drifting through space as dense, city-sized balls of degenerate matter. We can only detect the ones that are spinning fast enough, or accreting material, or close enough to us. The true neutron star population is largely hidden. This also means that the Milky Way contains a very substantial amount of mass locked up in neutron stars. Each neutron star represents between 1 and 2 solar masses of material essentially permanently sequestered. It is not going to be recycled into new stars on any timescale relevant to the current era of star formation. In some sense, neutron stars are the universe's inert nuclear waste, matter that has been processed, compacted, and stored. The total mass of neutron stars in the galaxy is uncertain, but estimated to be on the order of a few billion solar masses, comparable to the mass of all currently burning stars. Over billions more years, as more stars die and leave neutron star remnants, this proportion will only grow. In the very far future, on timescales of trillions of years, as star formation gradually exhausts the available gas, the stellar content of the galaxy will increasingly be made up of cold, invisible remnants, white dwarfs, neutron stars, and black holes, with the last generations of dim red dwarfs still burning. There is also the role of neutron stars in generating the diversity of heavy elements we observe. The R process in neutron star mergers does not produce all heavy elements uniformly. Different nuclei are produced in different proportions depending on the neutron flux, temperature, and timescale of the IR process event. The detailed abundance patterns we observe in metal-poor stars, ancient stars that preserve the chemical fingerprints of the earliest nucleosynthesis events in the galaxy, are a record of these individual neutron star merger events from the early universe. The field of galactic chemical evolution attempts to reconstruct this history. How many mergers occurred, at what times, where in the galaxy, what was their mass distribution? The discovery of extremely metal-poor stars with high R process enrichment, stars like the one called J0954+5246, which has an extraordinarily high abundance of europium, and other R-process elements tells us that a single neutron star merger can enrich the surrounding gas significantly enough to leave a chemical signature billions of years later. This is another sense in which neutron stars are connected to our existence. The planet Earth contains heavy elements, including the uranium and thorium, that drive Earth's geological activity through radioactive heat generation in the interior, keeping the mantle convective and the tectonic plates moving, which in turn cycles carbon and maintains a habitable surface environment. That uranium and thorium came from R-process events, from neutron star mergers in the history of our galaxy. Without those mergers, Earth might be geologically dead, with no plate tectonics, perhaps with a thinner atmosphere and a surface less hospitable to the kind of long-term habitability that may have been necessary for complex life to evolve. There is something deeply humbling about tracing the chain back from our daily existence to these extraordinary objects. The quantum mechanical principle that prevents your fingers from passing through your desk when you type, the same principle that keeps electrons in distinct atomic states, that gives chemistry its richness, is the same principle operating on neutrons that holds a city-sized ball of nuclear matter together across billions of years in the darkness between the stars. And the cataclysmic collisions of those balls of nuclear matter produced the heavy atoms that now comprise the planet we live on, the instruments we use to study the sky, and the bodies that allow us to look up and wonder. But let us also think for a while about the observational history of neutron stars in more depth, because the way we came to understand these objects is a scientific story that rewards attention. It is not a clean, linear progression from hypothesis to confirmation. It is a story of theoretical predictions being ignored, observational surprises being misinterpreted, and moments of sudden clarity separated by decades of confusion. The idea of a neutron star predates its observational discovery by more than 30 years. In 1933, just 1 year after James Chadwick discovered the neutron itself, Walter Baade and Fritz Zwicky proposed that supernovae might result in the formation of a star composed entirely of neutrons. They wrote, in a remarkably prescient paper, that such a star would have a very small radius and an extremely high density. They were essentially correct, and their proposal was based largely on energetic reasoning. The enormous energy released in a supernova could be explained by the gravitational potential energy released in the collapse of a stellar core to nuclear densities. For the next 3 decades, neutron stars remained a theoretical curiosity. The theoretical framework for understanding them was developed. Oppenheimer and Volkoff's calculation of neutron star structure in 1939 being the most important contribution, but there seemed to be no observational way to detect them. A cold, dark object 20 kilometers across at stellar distances would be invisible to the instruments of the time. It was radio astronomy that changed everything. By the 1960s, radio telescopes had developed to the point where they could detect faint cosmic signals, and in 1967, Jocelyn Bell Burnell stumbled on the first pulsar. The discovery story is worth telling in more detail than we have given it, because it illustrates something important about how science actually works at its best. Bell was a graduate student at Cambridge, working under Anthony Hewish on a new radio telescope, an enormous array of wires strung across 4.5 acres of English countryside, designed to study the scintillation of quasars. Bell's job involved analyzing miles and miles of chart paper output from the telescope, looking for interesting signals. It was painstaking, detail-oriented work that many might have been tempted to skim through. Bell did not skim. She noticed a small patch of what she called scruff on the chart paper, a regular, rapid pulsation that appeared during a specific part of the sky and reappeared each time that part of the sky was overhead. Her first instinct was that it was man-made interference of some kind, television stations, military transmissions, machinery nearby. She worked systematically to rule out these possibilities. What she could not rule out was that it was natural and astrophysical. As the weeks went on and the signal persisted, Hewish and Bell and their team became increasingly certain they were looking at something real, and the precision of the pulse timing, The signal repeated with a period of 1.337 seconds, steady to 1 part in 10 million, made it unlike anything previously known in astrophysics. When a second similar source was found in a different part of the sky, the LGM hypothesis became untenable. The explanation that emerged, a rotating neutron star, was quickly accepted because it fit so cleanly. Thomas Gold at Cornell proposed in 1968 that the pulsar was a rotating neutron star with a strong magnetic field, and that the pulses were caused by the rotating beam of electromagnetic radiation sweeping past Earth. He made a specific prediction: pulsars should be slowing down because the rotating magnetic dipole radiates energy, taking angular momentum from the rotation. This prediction was quickly confirmed. The confirmation of the neutron star explanation came spectacularly with the discovery of the pulsar in the Crab Nebula. The Crab Nebula is the remnant of a supernova observed by Chinese and other astronomers in 1054 AD, a stellar explosion bright enough to see in daylight for nearly a month. At the center of that expanding cloud of gas and dust is a pulsar rotating 30 times per second, slowing down at a rate entirely consistent with the energy output of the nebula. The pulsar is powering the nebula's glow through its spin-down energy. This was a direct, unambiguous link between pulsars and the remnants of stellar explosions, confirming Bardi and Zwicky's 1933 prediction in a deeply satisfying way. Since that discovery, pulsar astronomy has grown into an entire subdiscipline of astrophysics. More than 3,000 pulsars are now known in our galaxy. They are used for precision tests of general relativity, the double pulsar system PSRJ 0737-3039, discovered in 2003, has provided tests of strong field general relativity with better than 0.05% accuracy, confirming predictions of the theory with extraordinary precision. They are used to study the interstellar medium because the pulsar signal is dispersed by free electrons along the line of sight, and this dispersion measures the column density of electrons between us and the pulsar. They are used to probe extreme physics, as we have discussed, and they function, increasingly, as a galactic-scale gravitational wave observatory. The International Pulsar Timing Array and its partner experiments, the North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Indian Pulsar Timing Array, monitor arrays of millisecond pulsars, searching for correlated timing residuals that would indicate the passage of gravitational waves. In 2023, these collaborations announced evidence for a gravitational wave background, a stochastic bath of low-frequency gravitational waves pervading the universe. The most likely source is the population of supermassive black hole binaries throughout the universe, spiraling together in the centers of merging galaxies. This detection, if confirmed as the field advances, will open an entirely new window on the universe at the lowest gravitational wave frequencies. All of this science traces back to Jocelyn Bell Burnell's patient analysis of miles of chart paper and her refusal to dismiss an anomalous signal as noise. The Nobel Prize in Physics in 1974 was awarded to Anthony Hewish and Martin Ryle for their work in radio astrophysics. Bell received no share of the Nobel Prize, a decision that has been controversial in the scientific community ever since. Bell herself has been remarkably gracious about this outcome over the decades. She has said that she feels a graduate student receiving the prize would have sent the wrong message about how science works, with prizes going to the head of a research group rather than its members. But the scientific community has recognized her in other ways. She has received numerous prestigious awards, including the Breakthrough Prize in 2018, where she donated the entirety of the $3 million prize to fund scholarships for underrepresented groups in physics. There is another episode in neutron star observational history that deserves telling: the discovery of the binary pulsar by Russell Hulse and Joseph Taylor in 1974, for which they received the Nobel Prize in 1993. Hulse was a graduate student searching for new pulsars, and he found one, PSRB 1913 +16, that behaved oddly. Its pulse period was not constant in the way expected. It varied slightly, in a regular pattern. Hulse realized that this was not intrinsic variability, but Doppler shifting. The pulsar was in orbit around an invisible companion, and as it moved toward and away from Earth in its orbit, the pulse frequency shifted just as the pitch of a passing siren shifts. The companion was also compact. The orbital size was smaller than the Sun's radius, meaning both objects fit within a region smaller than the Sun, yet the companion was massive. The most natural interpretation was that the companion was another neutron star, too old and slow rotating to be detectable as a pulsar itself. Taylor and colleagues then performed precise timing measurements of this binary pulsar over years. What they found was that the orbital period was decreasing. The two neutron stars were spiraling together, and the rate of the inspiral matched precisely the prediction of general relativity for the energy loss due to gravitational wave emission. This was the first indirect evidence for gravitational waves, 39 years before LIGO would directly detect them. The agreement between observation and theory was at the level of a fraction of a percent. It was, by any measure, one of the most precise confirmations of general relativity ever achieved. The Hulse-Taylor binary pulsar also demonstrated something important about neutron stars in binaries, that they are long-lived enough and stable enough that orbital evolution from gravitational wave emission can be tracked over decades with enough precision to measure general relativistic effects at the sub-millisecond level. The pulsar is an extraordinary clock, and the binary is an extraordinary laboratory. The binary pulsar system will eventually merge, but not for about 300 million years. When it does, it will produce a gravitational wave signal detectable by advanced detectors, or their descendants, and likely a kilonova. The heavy elements produced will drift through whatever galaxy exists at that time, eventually to be incorporated into new stars and perhaps new planetary systems. These long timescales are part of what makes neutron stars so interesting. They connect cosmic epochs. A neutron star formed in the early universe, in the first few billion years after the Big Bang, may still exist today, having cooled and faded to invisibility, but still present, still composed of the same nuclear matter, still held up by the same quantum mechanical principle. It is a relic, a fossil of an earlier cosmic era, persisting through billions of years of galactic evolution. We should also discuss, in more detail, the mechanics of how a neutron star's spin evolves over time, because this connects to several important physical effects and to the practical question of how we use pulsars as tools. A new pulsar is born spinning rapidly, typically at rotation periods of tens to hundreds of milliseconds, derived from the angular momentum of the collapsing stellar core. It also has a very strong magnetic field. The combination of rapid rotation and strong magnetic field produces a powerful magnetospheric emission mechanism. Charged particles are ripped from the surface, accelerated to relativistic energies, and channeled by the magnetic field into the pulsar wind and into the beamed emission we detect as radio pulses. But this emission carries energy. The pulsar is radiating, and the energy comes from the rotational kinetic energy. As the rotation slows, the energy output decreases. The pulsar has a spin-down luminosity, a power output proportional to the spin-down rate, which depends on the magnetic field strength and the rotation rate. A young, fast pulsar like the Crab, 30 rotations per second, slowing at about 4.2 nanoseconds per day, has a spin-down luminosity of roughly 5 times 10 to the 38 watts, about 125,000 times the luminosity of the Sun. This energy output powers the Crab Nebula, causing it to glow. As the pulsar slows, both its spin-down luminosity and its radio emission weaken. Eventually, after millions to hundreds of millions of years, the pulsar slows to the point where its electromagnetic emission ceases. It crosses what is called the death line in pulsar parameter space, beyond which the mechanism for generating radio emission no longer operates. It becomes a dead pulsar, no longer detectable by radio telescopes, unless it is in a binary and can be recycled, as we discussed. In that case, accretion spins it back up and a millisecond pulsar is born. with a much weaker magnetic field. The accretion process somehow degrades the magnetic field, possibly by burying it under the accreted material, but a rotation period of milliseconds rather than seconds. These recycled pulsars can remain detectable for billions of years. Their slow spin down easily tracked over decades of observation. The very precise timing of millisecond pulsars has one more application worth mentioning: tests of exotic physics. Some theories beyond the standard model of particle physics predict the existence of ultralight particles, axions, or other dark matter candidates that could couple to the motion of a pulsar, either through direct interaction or through gravitational effects on the pulsar's orbit, if dark matter clumps are present. Millisecond pulsar timing arrays are sensitive to these effects and set constraints on such theories. The pulsars function not just as astrophysical objects of intrinsic interest, but as precision instruments for particle physics. There is also the theoretical frontier of what happens to matter at the very center of a neutron star at the highest densities, a topic we touched on earlier, but worth expanding. The challenge is that we are asking about matter at densities 5 to 10 times nuclear saturation density, and at these densities, the effective field theory approaches that work at lower densities begin to break down. The relevant degrees of freedom may no longer be neutrons and protons, but quarks. In quantum chromodynamics, the theory of the strong nuclear force, there is a property called asymptotic freedom, discovered by Gross, Politzer, and Wilczek in 1973, for which they received the Nobel Prize in 2004. Asymptotic freedom means that at very high energies or very short distances, the strong coupling constant, the strength of the interaction between quarks, decreases. At extremely high densities, quarks are so close together that the interaction between them is weak, and they behave almost like free particles. This means that at high enough density, the ground state of matter is not a neutron fluid, but a quark fluid, 3-flavor quark matter, or possibly 2-flavor quark matter if the strange quark mass penalty outweighs the energy gain from having 3 flavors. The transition from hadronic matter, neutrons and protons, to quark matter occurs at some density that we cannot precisely calculate because it falls in the strongly coupled regime where neither nuclear effective field theory nor perturbative QCD is reliable. What we can say is this: if the central density of a neutron star exceeds the hadronic to quark transition density, the core of the neutron star contains quark matter. This quark matter would be in a color superconducting phase. Quarks would pair up and condense analogously to electron-Cooper pairs in a conventional superconductor, but with the pairing being in color space rather than ordinary spin or momentum space. Various color superconducting phases have been proposed. The color flavor locked phase, where quarks of all 3 colors and all 3 flavors pair symmetrically, the 2-flavor color superconducting phase, and others with more exotic pairing patterns. Each of these phases has different thermodynamic properties, different transport properties, and different equation of state, and therefore different implications for neutron star structure. They also have different cooling properties. The color flavor locked phase suppresses the Urker cooling process, while some 2-flavor phases enhance it. The cooling curve of a neutron star with a quark core would therefore look different from one without, potentially providing an observational discriminant. The most exciting near-term prospect for resolving the quark matter question may come from gravitational wave observations. When 2 neutron stars merge, the hypermassive neutron star remnant, if one forms before collapsing to a black hole, oscillates at frequencies determined by its equation of state. If the remnant contains quark matter, its oscillation frequencies would be shifted relative to a pure hadronic remnant. Next-generation gravitational wave detectors, sensitive enough to detect this post-merger signal, could in principle see this difference. We would be, quite literally, using gravitational waves to do spectroscopy on the interior of the densest matter in the universe. The whole edifice of neutron star physics is, in a way, a testimony to the power of combining extreme observations with fundamental theory. Every discipline contributes: radio astronomy for pulsar timing, X-ray astronomy for surface temperature and pulse profile measurements, gravitational wave astronomy for mass radius constraints and merger dynamics, nuclear physics for the equation of state inputs, quantum field theory for the microphysics, general relativity for the macroscopic structure. It is one of the most genuinely interdisciplinary problems in all of physics. The study of neutron stars is, in this sense, not just a curiosity of high-energy astrophysics. It is a lens through which we see the deep connections between the laws governing the smallest scales of nature and the largest structures in the universe. It is an ongoing conversation between theory and observation, between quantum mechanics and general relativity, between what we know and what we are still working out. We are in a golden era for neutron star science. The detection of gravitational waves from neutron star mergers has opened an entirely new observational channel. NASA is providing high-quality radius measurements. Radio telescopes are discovering pulsars in exotic systems. Nuclear physics experiments on Earth are probing the symmetry energy of dense matter with increasing precision. Theoretical calculations using chiral effective field theory and lattice QCD are converging on more reliable predictions, and the questions that remain open are genuinely profound. Does the core of a neutron star contain free quarks? Do hyperons exist in neutron star interiors? What is the maximum mass a neutron star can reach? Is there a family of exotic compact objects between neutron stars and black holes, or is the transition direct? Could Bodmer-Witten strange quark matter be the true ground state? And if so, are there strange stars in the universe? Each of these questions is answerable in principle, with better observations and better theory. Some will likely be answered within the next decade. Others may require technological capabilities we have not yet developed, but the trajectory is clear. We are systematically pushing back the frontier of our understanding of matter under the most extreme conditions the universe can create. A neutron star is gravity's near victory. It is the point where gravity has won every battle except the last. It has compressed matter past the point where electron degeneracy pressure can help. It has converted electrons and protons into neutrons. It has created densities beyond anything in ordinary experience. And yet, it has been stopped, held at bay by the most fundamental principle of quantum mechanics. The neutron star says, "I am the limit. I am what matter looks like at the edge of its existence as matter. Beyond me is a black hole, where gravity wins completely and space-time curves so severely that even light cannot escape. But I, at least I, am still matter. I am still neutrons, quarks, nuclear forces, quantum states. I am still part of the physical world that can be probed and measured and understood. And I have been sitting here, stable, for millions or billions of years, waiting for beings with radio telescopes and gravitational wave detectors to figure out what I am." That figuring out continues, and it is one of the great intellectual adventures of our time. The universe is more structured, more layered, more interconnected than it appears from our ordinary vantage point on the surface of a medium-sized rocky planet around a middle-aged star. Beneath the apparent simplicity of starlight and darkness lies this extraordinary physics, Fermion degeneracy, and nuclear forces holding city-sized balls of nuclear matter together for billions of years, spinning at hundreds of revolutions per second, generating magnetic fields that would tear apart atoms at thousands of kilometers distance, emitting beams of radio waves and X-rays that cross hundreds of light years to our instruments and carry encoded within them the story of matter at its most extreme. We are living in the moment when that story is being read, when the instruments have become sensitive enough, the theoretical tools powerful enough, the collaboration between observational disciplines broad enough that the secrets of neutron stars are finally yielding to inquiry. It is an extraordinary moment to be paying attention. The next time you look up at the night sky, at the dense star field of the Milky Way arching overhead, at the faint smudge of a distant nebula, at the steady light of a familiar star, consider that scattered among those stars, invisible to the naked eye, are these extraordinary objects, city-sized, hyperdense, spinning, pulsing, seething with exotic physics, each one a monument to the battle between gravity and quantum mechanics, each one stable only because the universe forbids two neutrons from occupying the same quantum state, each one a cosmic data point in our ongoing effort to understand what matter is, what it can be, and what rules govern it at the boundary of its existence. And consider that some of the atoms in your body, the iron in your hemoglobin, perhaps some of the gold in any rings you wear, the strontium in your bones, passed through the interior of a neutron star or were forged in the fire of a neutron star collision before being scattered through the galaxy, swept into a gas cloud, incorporated into a solar system, deposited on a rocky planet, cycled through geochemistry and biochemistry, and eventually assembled into a living organism asking questions about where it came from. We are, in the most literal sense, connected to neutron stars, not metaphorically, not as a poetic device, but physically, chemically, historically. The quantum mechanical rules that govern them govern us. The nuclear physics that defines their structure produced our atoms. The gravitational waves from their mergers pass through our bodies at the speed of light, right now, from events that occurred millions of years ago. The universe is not a distant spectacle. We are inside it, made of it, governed by it, and the study of its most extreme objects, neutron stars among them, is not an escape into abstraction, but a deepening of our understanding of what we are and where we came from. That is the story of why neutron stars don't collapse. It is a story about quantum mechanics and nuclear forces and general relativity. But it is also a story about chemistry and planets and life, about the rules of the universe and how they apply at every scale, from the quarks inside a neutron, to the atoms in your hands, to the stars in the sky, to the gravitational wave ripples crossing billions of light years of space. The neutron star holds its ground because the universe will not allow otherwise. And in that refusal, that quantum mechanical, principle level refusal, we find one of the deepest truths the universe has to offer, that the same laws that govern the small govern the large, that the same mathematics describes both an atom and a stellar remnant, that we live in a cosmos of profound and beautiful coherence that is worth taking a moment to appreciate, that in all its density and all its strangeness is the universe we live in. And perhaps the deepest insight of all is one of scale and equivalence. When Pauli wrote down the exclusion principle in 1925, he was trying to explain why electrons in atoms fill shells in the way they do, why the second shell holds 8 electrons, why atoms have the chemical identities they have. He was not thinking about stellar remnants. He was not thinking about objects with more than a solar mass of material in a sphere 20 kilometers wide. The application to white dwarfs came a few years later in the work of Ralph Fowler. The application to neutron stars came a decade after that in the hands of Oppenheimer and Volkov. This is how physics works at its most powerful. You discover a principle in one domain, in the structure of atomic spectra, in the patterns of the periodic table, and you find that the same principle, applied in a completely different regime, governs objects on a vastly different scale. The principle does not change. The scale changes. The context changes. But the mathematics is the same, the underlying physics is the same, and the predictions that flow from it are confirmed by observation. This universality of physical law is the great bet that science has made on the structure of the universe, and the universe consistently has honored that bet. The same gravitational constant governs the orbit of a satellite around Earth and the merger of 2 neutron stars a billion light years away. The same quantum mechanical rules that determine the energy levels of hydrogen atoms in a laboratory on Earth determine the emission spectrum of hydrogen in a galaxy formed when the universe was a fraction of its current age. The same nuclear forces that can be probed in a particle accelerator in Europe are the forces that determine whether a neutron star will have a maximum mass of 2 solar masses or 3. When you look at a neutron star, or rather, when you detect its radio pulses with a telescope, since looking at it directly is not an option, you are encountering the application of every major branch of physics simultaneously. Quantum mechanics governs its internal structure. Nuclear and particle physics determine its equation of state. General relativity shapes its gravitational field and the behavior of space-time around it. Thermodynamics describes its cooling. Electrodynamics produces its pulsar emission. Statistical mechanics underlies the behavior of its degenerate matter. there is no more complete natural laboratory for fundamental physics in the observable universe. This is why physicists and astronomers who study neutron stars tend to speak about them with something approaching reverence, not mystical reverence, but the deep appreciation of someone who recognizes that they are looking at a place where everything they know is being tested simultaneously at its extreme limits by nature herself conducting an experiment that we cannot replicate and can only observe. A neutron star does not collapse because the universe has built into its deepest mathematical structure a prohibition against the overlap of identical fermions. That prohibition is not a rule that was added to make the universe work out conveniently. It emerges necessarily from the combination of quantum mechanics and special relativity, from the geometry of how fermionic fields transform under Lorentz transformations, from the antisymmetry of many fermion wave functions. It is, in the most literal sense, unavoidable, given that quantum mechanics and special relativity are true, and every experiment ever conducted confirms this. The Pauli Exclusion Principle follows with mathematical necessity, and from that mathematical necessity follows the existence of atoms, chemistry, life, and neutron stars. The same rule, the same necessity, the same universe. That is the story of why neutron stars don't collapse, and it is, in the end, a story about why we exist to ask the question,